Hello everyone. In this video, we'll be focusing on the topic of acids and bases. More specifically, how to identify the most acidic hydrogen in a compound. But first, before we start, we must first understand what an acid and base are. An acid can be identified as a molecule that has the ability to donate hydrogen from its structure, while a base is a molecule that is able to accept this donation. By that, the electrons between these two bonds, this bond of a hydrogen and oxygen, is being transferred from there onto the oxygen. While that's going on, the electron pairs here takes that hydrogen away from it. And by that, we can identify this to be our base, and this as our acid. These two structures are involved in specific reactions known as acid-base reactions, which start with an acid and base as reactants, and results in a conjugate and acid and base as the products. So after this transfer, our now products will be a conjugate base from this acid become a conjugate base, and that base will now become our conjugate acid. This is known as the Bronsted-Lowry acid-base theorem. Bronsted-Lowry. Theorem. For an acid-base reaction to occur, the acid on the reactant side must be deprotonated by the base. This leads us to our question stated at the beginning of this video. How do you identify what hydrogen in the acid will be removed to start an acid-base reaction? Let's start with this compound. The first thing you'd want to do is to draw in your missing lone pairs on the structure, which will be this oxygen and nitrogen. Since carbons are already bonded in full octet, these two also need to get to a full octet. Next, you should consider drawing the conjugate base of the molecule so that the molecule itself will contain a negative formal charge, indicating it is a strong conjugate base of this acid. So from that, we have our acid here. Since it has two hydrogens down here and three up here, that could be deprotonated, thus leaving us with this. Now let's draw in our conjugate. So from this structure right here, we're only going by electronegativity on which one of these are more electronegative. And on the periodic table, the oxygen is more electronegative than the nitrogen, meaning that this one could handle a more negative formal charge By that, I mean it can handle an extra pair of electrons than a nitrogen could. Since, of course, it'll still retain a full octet, while nitrogen would not be able to. From that structure, you can determine that the oxygen atom of the acid contains the most acidic hydrogen. As oxygen conjugate base contains a negative formal charge once it has been deprotonated. So, as our conjugate base, you can determine that to be our more acidic hydrogen. Let's try another one. First, we draw our lone pairs, which of course will be on this oxygen, and this one too, and this one as well. Carbon already is full, so that doesn't need any more. Now this time, we can already see that the most electronegative atom that are bonded to the hydrogen in this structure is oxygen. But we have 3 of them. How do we decide which one of these contains the most acidic hydrogen? In this example, we can determine this by drawing the resonance structures from the deprotonation of each hydrogen, such as from here and here. So, once we lose these, we will be getting this. And from that point right here, we can determine which one has the most acidic by drawing resonance structures after the protonation, as already said. So from the bottom oxygen on the left, once you move that formal charge, or I mean electrons, into the bond here, that will be giving you, of course, double bonded, double bond. And so from that point, no other resonance structure can be drawn. While in this one, the electrons are transferred to this bond, making this a double bond. However, because of that, there's a double bond right here clashing with this new one. So we'll have to move this one as well into the next one. And while that goes over there, it pushes this double bond onto the other. And from that point, that will push this double bond, or at least the electrons from this double bond, onto the oxygen. And since, oops, forgot to add formal charges. Forgot to add the lone pairs. But because now this has an extra pair of electrons, this will have a negative formal charge right down here. As we can see here, there's only one resonance structure that can be drawn for this oxygen, while the other would not give any since the charge would not be present. And because of that, our most acidic hydrogen would be from the top here. So this is where we'll get are most acidic, since it can make these resonance structures, while this one, it can't form any others at all, so wouldn't be likely at all for that to even have any acidic hydrogen in there, or at least form any resonance structure at all. Here's one more example. As we already know, we draw our lone pairs first. One, two, three, 4, 6. There we go. And now we see that most of the electronegative atom in each structure does not hold any hydrogens. And because of that, the only one we have are just the oxygens here, holding the hydrogens. So, how do we solve this? The method we use for this, of course, would be induction effect. Induction can be simplified as a highly electronegative atom's pull of electrons from a negatively charged atom or acid that is in close proximity to it. So, of course, once we deprotonate this, goes down here. These will have our electronegative. Our formal negative formal charge. So now at this point, we must focus on our halides, since of course these structures are almost identical except for the halides that are present. So now, out of all these halides, which one would be the most electronegative? And on the periodic table, that would be the chlorine. Because oxygen will retain a negative formal charge from the loss of its hydrogen, the chlorine atom will pull the electron density of the oxygen towards it. So, that'll be pulling it towards here, not towards the electrons, but the atom itself. Yeah. So because of that, it will help spread out the charge a bit. We can say that this structure contains the most acidic hydrogen because of this. Although the others do pull it, the oxygen, and help disperse it, it would be actually more of chlorine, since of course it has a stronger pull. Now, when determining the most acidic hydrogen, we must take into account where the most electronegative atom the hydrogen is bonded to, possible resonance structures that can be made, and inductive effects. But if faced with all three, resonance surpasses inductive effects. The reason for this is because electron density is not being delocalized from an electronegative atom that was deprotonated. Instead, it's just the electron density is just being kind of dispersed, or more or less how I say it, spread out. So although it does maintain a negative normal charge, just electron density is being spread out. So it's kind of making it a little bit more stable. Inductive effects, though, or induction effects, would be second to finding the most electronegative atom that the hydrogen is bonded to. The reason it being is because reason being is because since electron density is not being delocalized from the electronegative atom that was deprotonated, it would be very unstable. Hence why this would be the third. Well, the first major focus would be the resonance, if you can draw any at all. And that's how you can solve for the most the most acidic hydrogen in the structure of acid and base